The dif dix notation can be a bit clunky, so let's introduce some alternatives. To set up, let's suppose that f is a function of n variables, and let's call those variables x1, x2, all the way through xn. Then each of the following represents well-known notation for the partial derivative of f with respect to x sub I. First up is our usual dif dx notation, followed by this slick notation here, which avoids the spacing of a large fraction, but is still totally unambiguous. And in the spirit of minimizing notation, we might even get rid of the variable name itself, just indicating that we're differentiating the ith variable. Finally, my least favorite notation is to get rid of the derivative symbol completely and hope that your reader just understands what you mean. For our purposes, we're going to work exclusively with these first two. Now you've seen that it doesn't always make sense to talk about the derivative of a function. Not all functions are differentiable. This is actually much more complicated in several variables, but we still need some idea of when it's okay to talk about taking partial derivatives. We'll thus say that if f is a function of n variables, that f is c1 at the point A if all of its partial derivatives exist and are continuous at the point A. And there's a problem here, namely that we don't know what it means for a multivariable function to be continuous, but it effectively boils down to whether your functions are built out of the usual continuous functions like polynomials or exponentials. In fact, pretty much everything that we see is going to be C1. So with a C1 function, we can take whatever partial derivatives we like, and that sets us up for our next definition. Assuming that we have a C1 function of n variables, the gradient of f at A is the row vector of all possible partial derivatives of f evaluated at the point A. This weird upside-down triangle is sometimes called grad, or maybe del, or maybe nabla. And while this is the gradient at a point, we can of course talk about the gradient function, which outputs the gradient at each point. As an example, let's compute the gradient of the function f of xyz is x ln yz. Again, we won't worry about it too much, but f is c1 wherever it's defined, given that it's made up out of polynomials and logarithms. So all we have to do is to compute the partial derivatives. To make our lives a little bit easier, note that we can write ln yz as ln y plus ln z, which in turn means that we can write f of xyz as x ln y plus x ln z. And we don't have to do this, but if you want more practice, do this example again without taking this step, but it does give us the advantage that we can avoid using the chain rule down the line. At this point, we just start checking off derivatives. The x derivative doesn't even benefit from that simplification that we did a bit earlier, and with the y and z derivatives like so. In fact, we expect the y and z derivatives to look similar, right? The roles of y and z are effectively interchangeable in the definition of f, and so we expect their partial derivatives to similarly be related just by exchanging y and z. Putting these into a row vector gives us the gradient as so. So there's a very real sense in which for us, the gradient represents the derivative of f. This is because it has gathered all of the different derivative information about f into a single space.